All right, this is lesson 12.7a, graphing trigonometric functions for Honors Algebra 2. All right, so today, guys, we're going to be looking at how to graph a sine, cosine, and tangent function on the xy axis. All right, so first thing is that we learned in our last lesson that there are some graphs that are considered periodic, meaning they repeat after a certain amount. So it has like a pattern, it has a cycle. All right, so we're going to learn some vocab here today. So graphs of periodic function, I'm on bullet point number 1, have repeating patterns or cycles, and the horizontal length of each cycle is known as the period of the function. All right, so basically the horizontal length, how long it takes for it to start repeating itself and going into that pattern. All right, and then the next vocab word I want you guys to know is the amplitude. So the amplitude of the graph of sine or cosine equals half the difference between the max and minimum values of the function. All right, I'll go ahead and show you guys that when we get to an example. Notice that they don't talk about tangent. Tangent actually doesn't have an amplitude. It goes vertically and it goes up and down infinitely. So there is no actual value for that amplitude. All right, and tangent's also special here because it will actually have some asymptotes. All right, so let's just start with the sine graph first. So we're just going to talk about this sine graph right here, the parent function, where it's just y is equal to sine of theta. And we're going to consider theta to be in radians. All right, you can graph it in degrees, but we're going to just do the x-axis in radians right now. The domain is going to be all real numbers, and the range is going to be from -1 to 1, because that's the highest and lowest value that sine can be. All right, the amplitude is going to be 1. I'm going to show you that when we graph it. And the period is going to be 360 degrees if we were doing degrees, but in radians, that's going to be 2 pi. All right, so let's go ahead and look at this graph right here. And notice my x-axis is already in radians. Okay. All right, so let's go ahead and start graphing this. Now, you need to know your sine function pretty well. So if you know your unit circle, just imagine that you are taking that unit circle kind of like a fruit roll-up, if you guys have ever had a fruit roll-up before. And it's all spiraled up. And what we're going to do is we're going to unroll it along this x-axis, okay? So if you take your unit circle, if you have one handy next to you, that'd be really handy. So if it's like filled out, you can kind of see. And just remember, sine is the y coordinate, all right? So if you're looking at the angle at 0, sine, the value of y on that is also 0. So that's going to be my first point. All right. And then moving along at pi over 6, aka 30 degrees, sine is going to be at 1/2. All right, so let me go ahead and let's just mark this as 1 up here. And pi over 6 is 1/3 of the way to pi over 2. Okay, so halfway will be right around here. All right, at pi over 4, according to my unit circle, it's going to be at rad 2 over 2. Now, if I type that into my calculator, rad 2 over 2 is about 0.707. 0.707. So I'm going to approximate it right around here. All right. And then at pi over 3, according to my unit circle, I'm at rad 3 over 2. I'm going to punch that into my calculator, and that's about 0.866. So a bit higher, right around here. All right, and at pi over 2 is where I hit 1. All right, so we see, I'm going to smooth that out, connect those dots. All right, and that's what we have so far. Okay, and then we continue. So if we go on to 2 pi over 3, and then 3 pi over 4, and then 5 pi over 6, oops. Okay, we get those same values, and then at pi, we get 0. So we get the graph looking like that. All right, and then we continue at 7 pi over 6. Now we have negative 1/2. Okay, I'll mark my negative 1 right here. Okay, so like negative 1/2. All right, and then continuing that same pattern, I would get something right around here, and then at negative 1, or at 3 pi over 2, I get that sign is at negative 1. All right, connect those dots right there. Okay, and then continuing on, you can see we have that same pattern at negative 3, rad 3 over 2, negative rad 2 over 2, and then negative 1/2. Until at 2 pi, I am at 0. So again, I'm just following those coordinates on my unit circle. And instead of having my angle go around in a circle, my angle is actually going out on this straight line, the x-axis. Okay, and then after that, it starts repeating itself. So that is considered one period of the sine function. Okay, and what I want you guys to notice that's really cool is that you can see how these quadrants are marked out, right? So here we have quadrant 1, quadrant 2, quadrant 3, and quadrant 4. And according to our all students take calculus, right? For sine, it's positive in the first and second quadrant, negative in the third and fourth quadrant. And we can see that. It's positive above the x-axis, first quadrant, second quadrant, and then in the third quadrant we go negative, and then fourth quadrant's also negative. So you can see that it goes along with that unit circle. All right, let's go ahead and try it now for cosine. So let me go into blue. All right, so I'm going to do cosine in blue. All right, so same idea. Now if you look at your unit circle, cosine is the x-coordinate. All right, so we're going to use those same angles. All right, at 0 radians, the x-coordinate on the unit circle is 1. So here we're going to start at 1 and plot that point. At pi over 6, my unit circle, x-coordinate for cosine is rad 3 over 2. And remember the calculator told us that that was about 0.866. So it's right around here. And at pi over 4, it's at rad 2 over 2. So this is where it intersects that sine graph. At pi over 3, it is at 1/2. And at pi over 2, the x-coordinate is at 0. All right, and keep going. At 2 pi over 3, I'm at negative 1/2. At 3 pi over 4, I'm at negative rad 2 over 2. So we're just approximating here. And at 5 pi over 6, I'm at negative rad 3 over 2. And then at pi, I'm at negative 1. All right, and we just keep on going. So 7 pi over 6, negative rad 3 over 2. At 5 pi over 4, cosine is negative rad 2 over 2. See that intersection happen again with the sine. And then at 3 pi over 2, oh, whoops, I skipped one. At 4 pi over 3, I'm at negative 1/2. And then at 3 pi over 2, I'm at 0 again. All right. And you just keep on going. So now we're in quadrant 4. So at 5 pi over 3, I'm at 1/2. 7 pi over 4, at rad 2 over 2. And at 11 pi over 6, I'm at rad 3 over 2. And at 2 pi, I'm back at 1. All right, so let's go ahead and connect those dots. And we can see our cosine function. All right, so the cosine function that is in blue, and again, it follows that all students take calculus, where we have cosine is positive in the first quadrant, negative in the second, negative in the third, but positive in the fourth quadrant. So you can see that in the graph. We got positive in the first quadrant, negative in the second quadrant, negative in the third quadrant, and then positive again in the fourth. All right. And so this is just one snippet of the entire graph. This will keep on going on both ends. All right, so if you were to, let's say, zoom out on the cosine function, it would look like that. And it keeps on going, it keeps on going, it keeps on going. All right, so this is just one period. Now let me talk about the amplitude. So visually, the amplitude, excuse me, let's look at the sine function again, the red one, reddish green. The amplitude is this distance right here, right? So half the distance from the maximum to the minimum. Same thing with cosine. This right here is the amplitude, or you can look at this one right here is the amplitude. All right, so for the parent functions sine and cosine, both of their amplitudes are 1. All right, and since it's a measure of distance, they are always positive. Okay, let's go ahead and look at tangent. So for tangent, it's a little bit different. So again, if you look into your unit circle, you don't actually have the coordinates for tangent there. If you remember, tangent is going to be sine over cosine. And I think you guys learned that already. And if you didn't know that, well, now you know. All right, so tangent is going to be sine over cosine. So at each of these coordinates, we're going to go ahead and do the ratio of sine over cosine. All right, so starting at 0, I'm going to mark off 1 and negative 1 on my vertical axis. Oops. Negative 1. All right, so at 0, and you can even look to your two graphs right here. All right, so it's sine over cosine, so it's the red graph divided by the blue graph, all right, at each point. So here, the red graph is at 0, and the blue graph is at 1. So the ratio of 0 over 1 gets me 0. So tangent at 0 radians is at 0. All right, And I'm going to jump to pi over 4. Now at pi over 4, we see that sine and cosine are both at rad 2 over 2. So that gives me a ratio of 1. So it gets me a point right there. And then at pi over 2, sine over cosine, the y-coordinate over the x-coordinate, if you're looking at your unit circle, is 1 over 0. So actually that is undefined, giving us an asymptote. So we're going to draw a dotted or dashed vertical line at pi over 2. And this graph will actually approach that asymptote towards positive infinity. And this is why tangent has no amplitude. All right, let's go on to 3 pi over 4 right over here. And at 3 pi over 4, we have sine is rad 2 over 2 and cosine is negative rad 2 over 2. So we get a ratio of -1. And then at pi, we get a ratio of 0 over -1, which gives us 0. So this is how the graph approaches the asymptote on the right-hand side. All right, so continuing at 5 pi over 4. And we have a sine of negative rad 2 over 2, cosine of negative rad 2 over 2, giving us a ratio of 1. And then at 3 pi over 2, sine is -1, cosine is 0, so that gives us another undefined, giving us another asymptote at 3 pi over 2. And we see that this graph approaches now this asymptote, again on the left going up to positive infinity. Then at 7 pi over 4, we have sine is negative rad 2 over 2, cosine is rad 2 over 2, giving us a -1 ratio. And then at 2 pi, it's the same thing as 0. So we get another ratio of 0, giving us this graph going down to negative infinity on the right-hand side of this asymptote. All right. So now a couple of unique things I want you to notice for tangent. So again, like I said, there is no amplitude. Okay, so if it asks you for an amplitude, you can just say none. All right, so no amplitude. It also has these asymptotes. So that's unique compared to our sine and cosine graphs. And the last thing, and this is pretty important, you want to make sure you make good note of it, is that the period is actually not 2 pi in this case. The graph actually starts repeating itself halfway through. All right, so if you look, I kind of make a line right here. Notice the left-hand side and the right-hand side look exactly the same. So it actually started repeating itself once it got to pi. So that's unique also about tangent. So if you look up here, we see that our period is actually 180 degrees or pi radians. All right, so that is different for tangent also. All right, so those are your 3 parent graphs for sine, cosine, and tangent. Now let's go ahead and play around with these a little bit and look at what happens if we change the amplitude and we change the period. So in the equation, when you have a number multiplied in front of your trig function, that a right there, that will change the amplitude. All right, and the amplitude will be the absolute value of a, whatever that a number is that's being multiplied. And the period will change if you have a number multiplied inside the trig function. So being multiplied with your theta. So this one, like right here, let me find a color. this b right here. All right, so when it's multiplied outside the function, the trig function, it affects the amplitude. If it's multiplied inside the function, that affects the period. And how it affects the period? If you are in degrees, your new period will be 360 degrees, the original one, divided by the absolute value of b. If you're in radians, it's going to be 2 pi over the absolute value of b. All right, so let me show you guys a couple examples here. Okay, so for number 1, it says find the amplitude and period of each function, then graph the function. All right, so let's go ahead and find the amplitude and period first. So the amplitude is going to be the absolute value of what's being multiplied outside the function. So in this case, it is 4. And the period, and let's just do this in degrees. So the period is going to be 360 degrees divided by b. And in this case, your theta is being multiplied by 1/3. So 1/3 on that denominator gives me 1,080 degrees for that period. All right. And this is a cosine function. Okay, so I'm going to use my parent graph to help me see what kind of that basic pattern will look like. Okay, so because my amplitude is 4, on my vertical axis, I'm going to go up to 4 and down to -4. And since the period, how long it takes to start repeating itself, is 1,080, I'm going to mark that at the very, very right. And I'm going to mark off quadrants according to that. So halfway through would be 540. And halfway to 540 would be 270. And if I add 270 plus 540, that actually gets me 3/4 of the way, which is 810. All right, so make sure you mark those on your graphs because those are going to kind of hit those key points in the graphs that we need to have. All right. So if we look at our cosine graph, if you look at the shape, it goes from the top down to the middle, down all the way to the lowest number, and then it goes back up to the middle and back up to the top. So I'm just going to follow that shape with this graph. All right, and just hitting kind of those key points. So I'm going to start at the top at 4, then I'm going to go down to the middle, and then down to the lowest, -4, back up to the middle, and then back up top. And then just connect that with that wave shape. All right, and that's the sketch of your graph. And remember, it does keep on going, so I like to kind of show with arrows that it'll keep on going outside of that one period. Okay? All right, let me show you one more, number 2. Okay, so this is our tangent. So our tangent, starting with our amplitude, remember that there is none. All right, so even though there is a number being multiplied here, tangent goes up to infinity, it goes down -infinity, so there actually is no amplitude. For the period, got to be a little careful here. Tangent, the original period is 180. So I'm going to put 180 degrees in the numerator and divide it by what's being multiplied inside the trig function. So divide that by 2, giving us a period of 90 degrees. All right, so I found the amplitude, found the period. Now let's go ahead and graph. So I'm going to start, this is at 0 degrees. My period goes up to 90 degrees. I'm going to break this up into those 4 sections again. All right, and I don't want that to get too messy, so I'm not going to write those fractions in. And the amplitude does actually affect the graph, so I'm going to write 1/2 and -1/2 in on that vertical axis, just like I did in the previous example. All right, now look at the shape of one period of tangent. All right, so just one period, meaning I'm only looking from here to here. Okay. So it starts at 0, and then it goes up to 1, has an asymptote right in the middle, then it has the lowest, and then back to the middle. All right, so middle, up, asymptote, down, up. All right, so I'm going to follow that same pattern down here. All right, so middle, up, asymptote, down, and then up. All right, and then approach your asymptote, approach your asymptote. All right, and that is your tangent graph. Now I'm going to go ahead and draw arrows on these sides too, just to show that it does keep on going beyond that one period. Okay, why don't you guys go ahead and try it. So on the back of your notes or on the next page, try 3 and 4 and see how you do. Pause the video, and once you're ready, I'll have the answers for you. All right, so the answer for number 3, the amplitude I got is +4, because remember amplitude is a measure of distance, so it's always positive, and a period of 360. All right, since there is no b, or b is just equal to 1, that doesn't change the original period. All right, and then my graph, I'm just looking for those 5 key points on your graphs. All right, so at 0, I'm at 0. At 90, I'm at -4. At 180, I'm at 0. 270, I'm at 4. And at 360 degrees, I'm back at 0. And remember to mark those arrows showing that this is just a piece of the graph and that it does keep on going. All right, and number 4, for the amplitude, should be none because it's tangent. The period I got was 360 degrees. And here on my graph at 0, I am at 0. At 9 degrees, I'm at 2. Asymptote at 180 degrees. 270, I'm at -2. And at 360, I'm back at 0. All right, so that is one period. But again, remember, draw those extra arrows just to show that the graph does keep on going. All right, so the last thing I want to show you guys is this vocab term called frequency. All right, so frequency is defined as the number of cycles in a given unit of time. All right, so the number of cycles in a set unit of time. And the frequency of a graph is a function, the frequency of the graph of a function is the reciprocal of the period. All right, so it's the reciprocal of the period of the function. The period of the function tells you how long it takes to complete one cycle. So if we switch that around and do the reciprocal, that gives us the frequency, which is the number of cycles in a given unit of time. All right, so for example, very simply, if the period of a function is 1/40th of a second, then the reciprocal 40 is the frequency. All right, so the frequency is 40 cycles per second. All right, so that's how frequency and the period are related. So let's do an example. And here are some elephants. All right, and there you see my favorite animal, as you guys all know. And this picture, I actually took that picture when I was in Africa. My second time. That's like a mama and her baby calf. It's very sweet. They're very, very close to the car, which was cool. All right, so elephants. So I don't know if you guys know this, but elephants actually are able to hear frequencies, very, very low frequencies, okay? And they can hear as low as 5 cycles per second, or 5 hertz. Here it is. Frequency as low as 5 hertz or 5 cycles per second. Humans, we can just go as low as 20 hertz. But elephants can hear a lot lower. And so part A, it says find the period of the function that models the sound wave. So we want to find the period given the frequency. All right, so since we know the frequency is 5, let me write that down for my work. So frequency we know is equal to 5, and we want to find the period, which we know is the reciprocal of that frequency. All right, and so the period is 1/5 of a second. So put that unit on there for a cycle. Okay, so that's how long it takes for a cycle, is 1/5 of a second. All right, and then part B, it says let the amplitude equal to 1. Write a sine equation, okay, to represent that. All right, so we want to write a sine equation as to represent the sound wave y as a function of time t. All right, so that means my y axis is there, and there's my t in seconds for my graph. And then I want to graph the equation. Okay. And this is assuming that there's no phase shift or vertical shift. So let's go ahead and write the sine function first, and then we'll graph it. And in general, we know if we have no shifts, we have y is equal to a times sine of bt, where a affects the amplitude, b affects the period. And since they tell us that the amplitude is going to be 1, we know a is going to be 1. And the period, we need to find what b is. So b, we know, is related to period by taking the original, and I'm assuming they want us to do this in degrees. So the original period of sine is 360, so 360 degrees over the absolute value of b, and we could solve for b knowing that the period should be 1/5. All right. So solving for that, we get b is equal to 1,800. All right, and I'm also assuming that that will just be positive and that there's no reflection. Oops. So then we have a is 1, b is 1,800. So putting that back into this original general equation, that gets me y is equal to sine of 1,800 t. And that is my equation. All right, and let's go to the second part of this. So we have our graph. Okay, so the amplitude is 1. I'm going to mark that here, 1 and -1. All right, and then we already found the period up in part A. Is be 1/5 or 0.2 of a second. So I'm going to go ahead and mark that. You can do either 1/5. I'll go ahead and just do 0.2. Make it a little easier to divide. So this is going to be 0.1, 0.05, 0.15. All right, and we're just doing one cycle to fit in that one period. So I got my sine graph with my key points right there. Oops. And I'm going to continue with that arrow. Continue down here with that arrow. Alright, and there's my graph. Alright, and that is it for our lesson 12.7a. Mr. P will have a video for you for 12.7b, talking about some reciprocal trig function graphs.